Your CAN bus just bent bus off. Every message stopped. The vehicle is practically unresponsive. An engineer look at the log and see TEC 256. What caused it? How did it get there? And more importantly, how do you prevent it and recover from it? I have been analyzing CAN bus error on production vehicle for 7 years. In this video, I am going to show you exactly how every CAN error type works using a free simulator that I have built on AutoDevPro.tech. So let's get started. Before we inject error, let me tell you why this matter for your career. CAN bus error are in every automotive interview, not just for test engineer, for embedded developer, integration engineer, diagnostic engineer, anyone touching automotive ECUs. The question always come in this order. First, what are the 5 CAN type error? Second, what is TEC and REC? Third, what is bus off and how does recovery works? And the candidate who answer all three confidently and correctly, they get the job. By the end of this video, you will be able to answer all three in detail. Let me show you one by one. Here is our simulated CAN bus. 4 nodes: ECM, engine control module; BCM, body control module; TCU, transmission control unit; and the gateway. Every node start in error active state, TEC and REC below 128. This is normal operating condition. On the right, you can see TEC transmission error counter, REC receive error counter, both at 0. Notice there are 3 states a node can be in: error active green, error passive yellow, bus off red. We are going to move through all these states today. Error type 1, bit error. CAN has a unique self-monitoring feature while a node is transmitting. It simultaneously reads back what it put on the bus. If it transmits a 0 but reads back a 1, or transmit a 1 but reads back a 0, a bit error is detected. Watch the waveform. I injected 1 bit error from the ECM. See the waveform. The transmission is going normally. Then at the bit position 5, the error is detected. The node immediately stops transmitting and broadcasts an error frame. That 6-bit dominant sequence you see on the waveform. TEC goes from 0 to 8. Every CAN error incremented TEC by 8. Why 8? Because the CAN spec designer wanted faulty node isolated faster than they can recover. So, one successful transmission decrement TEC by 1. One error increment by 8. The math is force isolation. Stuff error. Error type 2. This is the most common error in real production system. CAN use bit stuffing. After 5 consecutive identical bits, 50 or 51, the transmitter automatically insert a complementary bit. This ensures enough signal transmission on the bus for receiver to stay synchronized. If 6 consecutive identical bits appear without that stuff bit, a stuff error is detected. Let me inject 5 stuff errors. Watch TEC. After 5 stuff error, it is already at 40. This is the most important thing to understand about CAN error handling. Error accumulate much faster than they recover. In real vehicle, stuff error are typically caused by electromagnetic interference, EMI. Long cable runs without proper shielding, motors nearby, alternator noise. If you see stuff error in a CAN log, check your harness routing first. Error type 3, CRC error. Every CAN frame contains a 15-bit CRC field. The receiver independently calculates CRC of the received data and compare it with the CRC field in the frame. If they do not match, then this is a CRC error. Notice something important about CRC error. Look at the counter. TEC stays the same. REC increases. This is because CRC errors are detected by the receivers, not the transmitters. REC is the receive error counter. It increased by 8 for CRC errors. This is the critical interview point. Bit errors and stuff errors affect the transmitter's TEC. CRC errors and form errors affect the receiver REC. Knowing which counter increase for which error, that is the detail that separates good engineer from the great one. CRC error in production typically indicate corrupt data, hardware fault, connector issue, or server EMI. So the next lined up is form error. Can frame have several fixed format fields? The CRC delimiter, the acknowledgement delimiter, and the end of frame. These must always be a recessive logic 1. If a dominant bit logic 0 appear in any of these fixed fields, a form error is detected. Form errors are relatively rare in production. When they do appear, they often indicate a hardware issue, a stuck transmitter, or a node with incorrect baud rate setting incorrectly interrupting frame boundaries. Again, REC increases, not TEC. Form errors are detected by receivers. This is consistent with what we saw in CRC errors. The next error is acknowledgement error. This is one of the most important error for embedded developers to understand. After a CAN frame is transmitted, there is one bit acknowledgement slot. Every receiver that successfully receives the frame must pull this bit dominant, that is 0. The transmitter checks this bit. If no receiver pulls the acknowledgement dominant, the bits stay recessive. The transmitter detects as acknowledgement error. TEC increases because this is transmitter detecting the error. When do you see acknowledgement error? 3 common situations. First, no other nodes are connected. The transmitter is alone on the bus. Second one, baud rate mismatch. The receivers are configured at a different speed and cannot decode the frame. And third one is the bus is broken. Open circuit, incorrect termination. In development and integration testing, acknowledgement error are the first thing you check when a node cannot communicate. If every frame gets an acknowledgement error, check the physical bus first. Now, let me show you the full journey from error active to bus off. I am going to inject 20-bit error from the ECM. Watch the state machine at the bottom. TEC is climbing 8, 16, 24 and so on till 128. There it is. The EMC transmission from error active to error passive. In error passive state, the node can still transmit and receive, but it sends a passive error flag instead of active error flag. A passive error flag is 6 recessive bit. Other node cannot detect this. The faulty node is becoming invisible. It cannot alert other about error it detects. This is the CAN specs intelligence isolation mechanism. Faulty node loses their ability to corrupt the bus before they fully disconnect. Now, let me eject more errors. TEC 200, 210, 220, so on till 256. Bus off. The EMC has physically disconnected from the CAN bus. In a real vehicle, this means the engine control module is offline. The vehicle will likely enter limp mode or stop responding. The dashboard will show multiple warning lights. The driver will feel it. Now, let's see bus off. A bus off node waits for 128 sequence of 11 consecutive recessive beats. Why 11? Because a complete CAN frame with interframe spacing has at least 11 recessive beats. Waiting for 128 of these sequence means the node waits for approximately 128 successful frame transmission on the bus before attempting to reconnect. This guarantees the bus is stable and healthy before the recovering node re-enters it. Sequence 32, 64, 96, 128 and it's complete. TEC reset to 0. ECM is back in error active state. The node is fully reconnected to the bus. In real system, bus of recovery can be automatic. The application layer trigger it immediately or manually, requiring a software command or ECU reset. Your test case must cover both scenarios. Now, one more concept that always comes in interview: CAN arbitration. Two nodes want to transmit at the same moment. They both start transmitting their CAN IDs simultaneously. Each node monitors their bus while transmitting. The rule is simple. Dominant bit 0 wins over recessive bit 1. So, the node with more leading zeros in its ID wins. Watch this. Node transmitting 1A0 and the node transmitting 1B2 both transmit their IDs simultaneously. Bit 10 down to 7 are identical. Both node continues. Bit 6, 1A0 sends a 0. 1B2 sends a 1. On the bus, the 0 wins. Dominant. 1B2 reads a 0 but it sends a 1. It detects it has lost the arbitration and immediately stops transmitting. It's become a receiver. 1A0 continue transmitting. This is a CAN non-destructive arbitration. No data is lost. The highest priority message always wins and no error are generated. This is not an error condition. It is a normal CAN operation. Now, let's discuss about some interview questions and answer. There are 6 interview questions at the bottom of the simulator. Let me give you the 3 most important answers. What are the 5 CAN error types? Answer. The bit error. Transmitter detects mismatch between send and the read bit. Stuffed error. 6 consecutive identical bits without a stuffed bit. CRC error. Checksum mismatch. Form error. Dominant bit it fixed recessive field. Acknowledgement error. No receiver acknowledged. Second one. What is the difference between TEC and REC? TEC. Transmit error counter. Increment when transmitter detects an error. Decrement by 1 per successful transmission. REC. Receive error counter. Increment when receiver detects an error. Both threshold 128 for error passive, TEC 256 for bus off. And last one. How does bus off recovery works? The node waits for 128 sequence of 11 consecutive recessive beats on the bus, then automatically transmit back to the error active with TEC reset to 0. This simulator is completely free at AutoDevPro.tech. No logging is needed, no installation is required. Every error type, all counter behavior, bus off recovery and arbitration, all are interactive. If this video helps you to understand CAN error in a better way, then please do consider subscribing our channel. Thanks for watching.